Let us talk about this problem. We are given a string. We need to construct longest proper prefix suffix array for this. We are calling it LPS here. This LPS array construction is a prerequisite for understanding KMP algorithm. It's a pre-processing step in KMP. We first construct this LPS array for the pattern. Let us first define what is a suffix and what is a proper prefix. So if we consider ABC as a string, its proper prefixes are empty string, A, AB. Please note that ABC is not a proper prefix. ABC is a prefix but not proper prefix. When we add proper word, it means the length of prefix should be smaller than the given string. What are the suffixes of ABC? Suffixes are empty string, then C, then BC, then ABC. These are the suffixes. Here is one more example to understand proper prefix and suffix better. Proper prefixes of ABCD are empty string, A, AB, ABC, right? ABCD is not included. Proper suffixes of this are empty string, then D, then CD, then BCD, then ABCD. So we are given a string and we need to find out longest proper prefix which is also suffix at every point. So first entry in this LPS array is always going to be 0 because for a string of length 1, you cannot have a proper prefix of length more than 0, right? So your first entry is always going to be 0. Your second entry depends whether these two characters are same or not. If these two characters are same, then it's going to be 1, otherwise it's going to be 0. For example, it's 1 here. Here it's 0, here also it's 0, here also it's 0. The third entry for ABA, what are the proper prefixes of ABA and what are the suffixes of ABA? Proper prefixes of ABA are A, AB and empty string. Suffixes of ABA are A, BA and ABA. So which of them are the longest and same? Only one, A, right? So our output is 1 for ABA. Let us now see the next value. For ABAB, our output is 2. You can notice that the longest prefix AB is also a suffix, so our output is 2. For this ABABC, the last entry for whole string, do you find any proper prefix which is also a suffix? No, so our output is 0. When all characters in a string are same, your LPS array is going to be like this, 0, 1, 2, 3, right? For all characters being distinct, all values are going to be 0. Let's see this example now. Your string is AB, AB, AB. First is always 0. Second is also 0 because the first two characters are not same. Third is 1 because there is a proper prefix which is also suffix. Fourth is 2 because there is a proper prefix AB which is also a suffix. Fifth one is 3 because there is a proper prefix of length 3 which is also a suffix. Sixth one is 4 because there is a proper prefix of length 4 which is also a suffix, right? So that's why we have the output as 4. Now here is an exercise for you to make sure that you understood the question really well. Please write down LPS arrays for this string and this string. Here are LPS arrays for these strings. We have 0 always for the first character, then for second also 0 if the first two characters are not same. In this example, we have 3 characters till this point and our output is 1 because there is a proper prefix A which is also suffix. Till this point, our answer is 0 because there is no proper prefix which is also suffix. For this, we have again answer 1 because A is there. For this point, we have answer 2, AB, AB. For this point, we have 3 answer ABA, ABA, proper prefix and suffix both. For this point, our answer is 0. Let's see this example. 0 for first two. For this one also 0 because there is no proper prefix which is also suffix. For this one, we have 1 because A is there. For this one, we have 2 because AB, AB matching. For this one, we have 3. Now please pause this video and think of a program that takes a string as an argument and builds LPS array for the input string. We are going to talk about 2 solutions for this problem. First is going to be our naive solution with time complexity as big O of nq, where n is the length of the string. And then we are going to talk about a linear time solution which is used in KMP algorithm. Let us now talk about the implementation of naive approach. Here I have written code. This code is written kind of pseudo-code, which is close to C++ and Java programming language. If you're programming in Java, the only thing that you need to change is instead of doing stri, you need to use str.char at I when you are using a string object. Okay, so this function, fill LPS function, takes a string as an argument, an LPS array as an argument, and what it does, it calls the above function for every index, and it uses the returned value of the above function to fill the LPS value for index I. This is the main function. This function takes a string and its length as arguments, and what it does is it simply returns the length of longest proper prefix, which is also suffix for this given string, right? So it works for only one string, and this function calls this function for every substring starting from 0 to n-1. So that's how these two functions work. Let us now see working of this function. So what this function does, it's a very basic function. For a string of length n, the maximum value of longest proper prefix, which is also suffix, can be n-1, right? Because you cannot have a proper prefix of length more than n-1. So this function basically tries every length starting from n-1. And as soon as it finds a proper prefix which is also suffix, it stops and returns that particular length. And if it does not find any length greater than or equal to 1, it returns 0 at the end. Now, how does this logic work? This part is explained here. Suppose we have this string to this particular function, right? So what it is going to do, it's going to start from length 7 because the total length of a string is 8. So it's going to try with 7 first, and then it's going to check is 7 a potential answer. So when you are checking for length 7, basically you need to compare this string with this string when you are at length 7, right? So what you need to do, you need to compare str0 with 1, str1 with str2, 0 with 1, 1 with 2, right? That's what you need to compare to check if this longest proper prefix is also suffix or not. For adjusting these indexes, we have written this logic. We compare stri. So these indexes simply go increasing from 0 to n-1, but these indexes grow from n-len. They begin with n-len, then we keep on adding I, where I starts from 0, right? So now we compare these two characters, and if we match all the characters, we say that, okay, we found this length as the longest proper prefix, which is also suffix, and we return that length. So these are examples. When you have length equal to 6, you will be comparing, you will be basically be checking this string and this string if length is 6, right? If length is 6, then you will be checking these two strings if they are same or not. If length is 5, then you will be checking these two strings if they are same or not. You will be checking this string with the last 5 characters of this string. So that's what we are doing in this logic. Now what is the time complexity of the solution? We have two functions in it, and this function calls the above function in a loop that runs big O of n times. We are running from 0 to string length -1. And this function has two loops, and these two loops run big O of n square time, where n is the length of a string. So we have a function being called inside a loop, and this function has time complexity big O of n square. So overall time complexity of the solution is big O of n cube. Now please pause this video and think of a solution that works in big O of n time. And the solution is really tricky. The idea of the solution is to use already computed LPS value. When you are at index I, you must have already computed LPS values from 0 to i-1. So rather than computing fresh LPS value for index I, you reuse the existing values and you compute this value using the existing values. Let us now talk about the efficient solution, which is used in KMP algorithm. This efficient solution is based on some basic ideas. This is first basic idea. And this idea is, if we know the length of LPS I-1 is length, and if str length and str I are same, then LPS for ith character is length +1. So this is our input string, and LPS value for this is length. right? Which means the characters from 0 to length minus 1 are same as characters from here to length, right? So this length and this length characters are same because LPS means longest proper prefix, which is also suffix. So this prefix is same as this suffix. Characters from this to I minus 1 and having length as length. So this is we know. Now this character and this character, they both are also same. It means your LPS of I is length plus 1. We can simply increment the length by 1. Let's understand this with this example. See, LPS of 0th character is always 0. So our length is initially 0. Now for the second character or index I equal to 1, we simply compare str I and str length. So I is 1, so we compare 1 with str 0, length is 0. They are same. So we do simply length plus 1 and assign it to LPS 1, which is 1. Now when we are at I equal to 2, our length is 1, right? Because this is the LPS value of 1, right? Now we are at I equal to 2. So we simply compare str2 with str of 1, str of length and str of I. They are same. So we make LPS2 equal to length plus 1, 1 plus 1, 2. And our now length is 2 for the next iteration. When we are at I equal to 3, we again compare str I and str length, which means we compare str3 with str2. They are same. So we make length LPS3 equal to 3 and length also equal to 3. There are no more characters, so we stop this. So using this idea, we could find LPS array for this example string in big O of n time. Now, how do we handle the case when str length and stri are not same? Let us now talk about the case when stri and str length do not match. This particular case has two subcases. The first subcase is len is 0. Please note that this len represents LPS value of index I minus 1, which is longest proper prefix, which is also suffix for your string starting from index 0 to I minus 1. So this is the case. Then there was no matching characters earlier because this is LPS I minus 1 and the current character also does not match with str0. Please note that str length is str0 because length is 0. So if these two are not matching, it means LPS is clearly 0 because this character is not matching at all with this character and LPS of this was also 0. Len is LPS of 0. Right? So this case is really simple. In this case, we simply assign 0 value to LPSI. This is interesting case when length is greater than 0, right? Else part. In this case, we recursively apply the LPS function to find out index of the next character that has to be matched with stri. So we compute the index as LPS of length minus 1. Please remember this length is length of the LPS value for I minus 1 index. So here this length represents the previous value of length, not the updated value. Updated value is this. This is the updated value of length. So let's understand what is the meaning of applying this function recursively and how does this work. This length is length of the LPS I minus 1, right? Value of LPS I minus 1, which means these characters are same as these characters, right? And we were trying to extend this prefix and suffix by comparing these characters, but they did not match. So what are we saying? We are going to now try matching the character at this index. LPS of length minus 1. That's what we are saying is our new length. Why are we using this index? The reason is these characters must be same as these characters because this is the value of LPS length minus 1, this particular index. And since this whole thing is matching with this whole thing, this string and this string, they must be same. So this proper prefix must also be a suffix here now. So that is why we try extending this proper prefix now. We try checking whether the next character just after it, the character at this particular index, if this matches with this particular character or not. Because if this matches, then we extend this particular LPS. That's the idea. So if LPS I minus 1 cannot be extended, then we find the redundancies within LPS len minus 1 and try extending using those redundancies. Let us now do a complete run of this algorithm for this example. Before we do this run, let's do a recap of the two ideas that we have discussed. The first idea is if stri and str length are matching, then simply do assign length plus 1 to LPS I and do length plus plus. Please remember, length is LPS I minus 1, LPS value previous index. If they are not matching, then there are two sub cases. If length is 0, then simply make LPS I equal to 0 because you have already matched 0th character with the current character and they were not matching. So LPS cannot even be 0, right? The second case is when length is greater than 0. In this case, you recursively apply LPS function. You use the value of LPS length minus 1 and you get a new length. Then you again compare stri with str length. You keep doing it while stri and str length, they are not matching and length is greater than 0. You stop when you see a match or when length becomes 0. Right? So that's a complete algorithm that we run for filling the LPS array. We will be talking about implementation details and detailed algorithm later in this video. Let us first cover this particular example to understand the two cases. We know that LPS 0 is always 0, right? The 0th character is always going to have LPS value 0, so we assign this value and we have initial value for length is 0. Now we are always going to compare stri with str length and then we are going to decide which case we are in. So what is our I now? I is 1. We are computing LPS for this. And what is length? 0. So we compare these two characters. They are not matching. So which case we are in? We are in this case. Length is 0 and they are not matching. So we simply assign it 0. Now we come to this index. Length is 0. And stri and str length, these two characters are not matching. So we simply assign 0 to it, right? Now we come to this index. We again compare stri and str length. These two characters, they are not matching. So we simply assign 0 to this also. Now we come to the next index. We again compare stri with str length. Please note that length has been 0 so far. At this point, stri and str length, they match. So what we do is we assign length plus 1 to LPS 4 and do length plus plus. So LPS 4 gets value 1 and length gets value 1. Now we compute LPS 5. When we come to LPS 5, we again compare stri with str length. We compare these two characters. They're matching. So we assign length plus 1 to this and do length plus plus. Now we come to this index. And we again compare stri with str length, right? They're matching. So we again fall in case 1. We assign the value length plus 1 to it and do length plus plus. Now we come to index 7 and we again compare stri with str length. Length is 3 now and I is this character. So we are going to compare these two characters. They do not match. So this time we see a mismatch after seeing some matches. Your length is greater than 0 and characters are not matching. So you fall in this case 2.b. And in this case, what you do is you find the new value of length using LPS length minus 1. What is LPS length minus 1? Length is 3, length minus 1 is 2. So LPS 2 is 0. So your length is 0 and stri and str length are matching. So when stri and str length they match, you are in case 1. And what we do in case 1? We assign length plus 1 to this and we increment the length by 1. So our length becomes 1. So this length in fact is of no use because there are no more characters after it. We stop at this point and we have computed all the LPS values. Let us now talk about implementation of this efficient approach. I have written a pseudocode here that takes a string as an argument and an LPS array as an argument. This code fills this LPS array for this string. This code is written close to C++ and Java programming languages. What do we do as a first line in this code? We find the length of the string. We initialize the length of previous LPS as 0. And we initialize LPS 0 as 0. Now we run a loop that begins with I equal to 1 and it runs while I is smaller than n. Inside this loop, we are going to first follow idea 1, and if they do not match, then we are going to follow idea 2, and we have two cases for idea 2. So idea 1 says, if str I and str length, they both are matching, simply do length plus plus and do LPS I equal to length and move to the next index. Idea 2 says that if they do not match and if the length is 0, simply make LPS I equal to 0 and make I plus plus. And if length is not 0, then update the length as LPS of length minus 1, which is recursively applying the LPS function again and again until we see a match or length does not become 0. So when I say recursively applying, it means it will keep on going into this iteration, it will keep on falling into this case until we end up falling this case or this case, right? Until the length becomes 0 or the characters do not become same, right? So we'll keep on falling into this case while length is greater than 0. Let's now do a dry run of this example for this particular string. So LPS 0 is always 0. LPS 1, we simply need to compare str length with stri. 0, 1, 1, 0 and 1, they match. So we are going to do length plus plus and assign it to LPS 1, right? So length becomes 1 and LPS 1 becomes 1. Now again str of length and str of I, they match for this I. So we again do length plus plus. We have LPS 2 is 2 and length is 2. Now when we come to I equal to 3, stri and str length, they do not match, right? So we fall into this case and we update the length as LPS of 1. And what do we get as a new length? 1. And again they do not match, right? So we update the length as LPS of length minus 1, which is 0 now. And again they do not match, but this time length is 0. So we make LPS of 3 is 0. Now we come to I equal to 4, and this time stri and str length, they match. So we make length equal to 1 and make LPS 4 equal to 1. This time again they match, So we keep on incrementing length and LPS. When we come to I equal to 7, they do not match. We are matching str of length, which is str of 3 with 7a, right? So they are not matching. And now length is greater than 0. So we fall into this main case again. And what do we do now? We make length equal to LPS of length minus 1, LPS of 2, which is 2, right? And now we again match, and this time this and this, they match, right? So we simply make LPS of 7 equal to length plus plus, right? And length now becomes 3 and LPS 7 also becomes 3. Now we move to I equal to 8. When we come to I equal to 8 case, our length is greater than 0 and the characters do not match, right? The character at LPS length is 3 now, they are not matching, right? So we fall into this case again and we update the length as LPS 2 and str2, it again does not match with this character. So we again update the length as LPS 1, again do not match. We update the length as LPS 0, again they do not match. This time we fall into this case and we make LPS of 8 as 0. So this is how we compute LPS array for this particular string example. Let us now talk about time complexity of this. Let's consider some corner cases first. What happens when all the characters are same? When all the characters are same, you are always going to fall into this case and you are always going to do I plus plus, right? So your time complexity is clearly theta n, because I begins with 1 smaller than n and always do I plus plus. Now let's talk about the case when all the characters are distinct. In this case, you are always going to fall into this case. Your LPS value is always going to be 0 and you are always going to do I plus plus. So this also needs theta n time. Now let's talk about the case when some characters matched and then there was a mismatch. When you have to execute this part. Like this example. These A's were matching, then there was a mismatch. These A's were matching and then there was a mismatch and then there was one more match. This particular case, when you fall in, it needs at most 2n work. You did X matches, right, or length matches. Then when you see a mismatch, you will again do at most the length matches again. So you did traverse n characters and at the most you are going to traverse all the n characters again. So overall, the time complexity of this particular solution is theta n. When you fall in this case, you may need 2n work, but this is also theta n.